let's move yeah, to the talk by Jonathan Feng about FASER.
Okay, can you see my slide and the cursor?
Yes.
Okay, very good. So yeah, thank you very much for the chance to talk. It's especially nice to talk at a session where, you know, pretty much all the other similar detectors are already represented by expert proponents. And so I'll just focus on FASER and then also talk about the forward physics facility, which is sort of a future proposal. So let me start with saying something that maybe is a little bit preaching to the choir, but I think it's something that needs to be said. A fact that should be better appreciated is that we are in a critical period. Here's the famous, plot of luminosity versus time at the LHC going into the high luminosity era, where of course here about to start run 3. But the point is, 20 times more integrated luminosity is in front of us. Yet if we don't do anything, it's in some sense not exploited. And in fact, if we don't do anything now to plan for this, significant changes will have to happen in the next, say, 6 years or so. If we don't plan for it now, we will lose these opportunities. And if they have to come at a future hadron collider, we may lose these opportunities for decades. Who knows when the next opportunity may be, 2045, 2060, 2075. I'll present some results about things like, for example, producing TV neutrinos, which literally, if you don't do something now, you will not have a chance to see these things for, till we are dead, to put it very, very bluntly. So what should we be doing now? There are many answers, of course, but one answer I think is extremely promising is that we should explore a rich BSM and standard model physics program in the far forward region that greatly expands the LHC physics potential with relatively little additional investment. So this is a plot which I think I won't dwell on here given the number of experts in the audience. But the point is simply that if you were to just be very agnostic about where the new particles are, you have strongly interacting heavy particles, which could be there, but you also have weakly interacting light particles, which could be there. And so far, at least in the last 3 decades, the interest has completely focused on strongly interacting heavy particles, namely, squarks and gluinos and TV extra dimensions and Technicolor and things. What really is lacked is the interest in the weakly interacting light particles, something at the MeV to GeV scale. And of course, if they have order 1 couplings, they would already be discovered like the electron. But if they're down here at the milli or micro sort of interaction length, interaction strength level, they wouldn't be discovered, but they could be if we're smart. And this sort of follows in the line of thinking of Fred Reines, who did not go work at giant colliders, but found neutrinos lying down in this part of parameter space. This is a purely particle physics way of looking at things. You can also look at it from a cosmological point of things, where you think about you have some hidden sector with some dark matter in it, and maybe it interacts via some portal like this A prime, this dark photon. And you can calculate the interaction annihilation cross-section. And parametrically, it goes as epsilon squared because there's some coupling here. And by dimensional analysis, it goes as 1 over the dark photon mass squared. And so then you can just simply ask where in this parameter space is the thermal relic density correct? And you find that up here, you have too little to be dark matter. It annihilates too quickly. Down here, you find that there's too much to be dark matter. And along this same diagonal is just the right amount to be dark matter. And that this diagonal coincides with the frontiers of high energy physics experiments, because there's the very famous WIMP miracle up here, which tells you that right here is a good place for relic density and also sort of at the edge of where we're looking at things at the LHC. But this parameterization tells you this goes down a diagonal of roughly slope 1 in this plane. And that's also a region where new experiments can probe. So it's just an incredible coincidence that the cosmological motivation and the particle physics motivation line up so beautifully in this plot. So now I'll just focus primarily on looking for the new light particles. If the only particles we have around are new and weakly interacting, existing LHC detectors are really perfectly designed not to see them. These detectors, like here's Atlas, are designed to find new heavy particles, which make things that are, to zeroth approximation at rest. They decay isotropically, and you get stuff going off with high PT. But light particles are primarily produced along the beamline. So they can be produced, as we saw in the last talk, in meson decays, pi, eta, etc. And these are dominantly produced along the beamline. So you have protons coming in, colliding here, and by far the majority of the interesting particles in this case are going straight back out the same holes that the protons came in. And that's exactly the part of the detector that is completely uninstrumented, and so they escape undetected. So, what do we do? Well, we can hope that these particles, a few of them will also be produced in Higgs decay and things. And of course, that's strong motivation for building things like Anubis and Methuselah and Codex B. But maybe the more straightforward thing is just to try to simply find these particles that go straight down the beamline. And so this is motivated by two things. One, this is where they mostly are. But two, the amount of cross-section there is enormous. So, when we're looking for fluinos with femtobarn cross-sections, we're completely ignoring the fact that there's a almost barn level cross-section, which is the inelastic cross-section of things going down here. So, 14 orders of magnitude higher cross-section is just completely wasted down the beamline. And so if we can look for particles here, they don't have to be produced in, say, every pion decay. They can be produced in every 10 to the 10 pion decays, and you still have an enormous flux of these new particles. And so that's basically the motivation for putting a new detector down here. So where should you put this detector? Well, you basically can take an interaction point like at Atlas or CMS or LHCb, anywhere you want, and draw a straight line along the beam collision axis. Obviously, you can't put a detector right here because that will block the proton beams. But if you go far enough away, the proton beams curve away and you can put a detector there to catch weakly interacting light particles. And that's what FASER did. We found a tunnel here, TI-12, which intersects the beam collision axis, more or less. It's in this transfer tunnel that was sort of a relic of the LEP days and is completely abandoned, or was completely abandoned until now. And so this is the view down underground, 85 meters below ground, looking west. So you're kind of standing here in this cavern called UJ12, looking west toward Atlas. Here's the proton beams coming from Atlas, which is 500 meters in that direction. New particles that are light will go straight, and they will basically be produced at Atlas, go straight, leave the LHC tunnel, pass through 100 meters of concrete and rock, and then emerge in this side tunnel, TI-12, going along this axis. And so the idea is to basically instrument that axis and see if you find any interesting new particles. And it's an extremely quiet location. As I said, you have 100 meters of rock and concrete between here and the Atlas IP. And so it's sort of like, a looking, what do they call it, a light through walls experiment where the wall is 100 meters thick. So the FASER timeline, I won't go into detail here, but basically the proposal was about 4 years ago. And through really enormous help from the Atlas SCT and LHCb collaborations, which lent us basically spare detector parts, And on the funding side, Heising-Simons and Simons Foundation, as well as really generous support from CERN for host lab costs, FASER was approved and built in a fairly short time. And as of 2 months ago, is now fully installed in the tunnel and is being commissioned right now. So let me show you that. So here's the plan for FASER. Basically, as I mentioned, you're looking into a 100-meter wall. And the idea is that some LLP, like a dark photon, will come along, not interact with anything, and then decay, most likely into E plus E minus. It then decays, and then we have magnets, which separate the positive and negative charge tracks. Then we have tracking stations here, which can detect those tracks. And we have a calorimeter at the back. So in the case that there are electrons, we can actually tell they're electrons and get some measurement of their energy. So if you have, two TeV charge tracks that come at the same time and point straight back to the Atlas IP through 100 meters of wall, that's a pretty strong signal of new physics. There are, for example, important backgrounds coming from muons. There were, roughly speaking, about a hertz of muons per centimeter squared that do make it through this wall. But we have scintillators here. As you can kind of see, here's the PMTs that come out, scintillators here, here. And we've shown that these scintillators are more than sufficient to veto these muons. So even with roughly 10 to the 9 muons in run 3, we have 4 layers of scintillator. Each scintillator provides a veto power of about 10 to the 4, 10 to the 5. So combined, it's 10 to the minus 20. So it completely kills off the muon background. So as I said, I'm skipping obviously lots of important, interesting details, but after 2 years, this detector was constructed and installed. Here it is. So here is the LHC, and if you go 480 meters that way, there's Atlas, and here's TI-12, and here is the FASER detector. This was taken maybe late last year, and this is the basically final detector as of 2 months ago. You see these blue magnets here, all these, cables, very complicated. Here's a calorimeter in the back, but anyway, it's completely installed. So we're commissioning it right now, starting with the first cosmic ray we discovered, within hours of finishing the construction. This was back in March 18. Here you see a cosmic ray passing through 3 tracker layers in 1 tracking station. We now have, hundreds of these event displays, but I won't show them to you. I found they're sort of like baby photos. They're fascinating to the parents, but not necessarily the most interesting thing to everyone else. But things are doing well, and we're very, very happy with how the detector's performing. So what do we hope to get? Well, here's a plot of FASER reach in the dark photon parameter space. Here's the dark photon mass from 10 to 100 MeV. Here's this epsilon parameter, and the gray is already excluded by other experiments. And these dashed colored contours are other experiments projections. But these yellow things and the lines, solid lines, are FASER's reach. And you see that even with 1 inverse femtobarn, which is something like, I don't know, a week or something of run 3, we start probing new parameter space here. And as time goes on, of course, we go farther and farther out into new parameter space. And so, I think this is kind of the point here. By looking at things in a different way, even with the first inverse femtobarn down here somewhere, we will start making headway into new parameter space and possibly discovering new physics. So without the detector upgrade, if we just simply have that detector as installed right now, the high luminosity LHC era will extend sort of the luminosity times volume, which is roughly speaking sort of a measure of the number of events, by a factor of 3,000 after the first inverse femtobarn, simply because we'll get 3 inverse attobarns by the end of it. And so that gives you a sense that these contours are, what does this actually mean? But what it actually means is by the end of high luminosity era, you could actually have thousands of dark photon events if nature were very, very kind to us. If we extend to FASER 2, which is a bigger detector, it's quite possible that we could extend this reach by a factor of 1 million, just because it's bigger and the high luminosity is, of course, has higher luminosity. Now, another interesting fact about FASER is that in addition to looking for new physics, we can also look at old physics, but in a pretty interesting new way, and that is neutrinos. So neutrinos are, of course, a known light weakly interacting particle. So if you're looking for light weakly interacting particles, what about neutrinos? The thing that's important to note is that we, of course, believe that neutrinos have been produced in vast quantities at many colliders, but not a single collider neutrino has ever been detected before last month. And so the point is that these neutrinos are, they're produced in W decay and things, but there are not that many of them. And of course, they interact extremely weakly. If you go in the forward direction, though, of course, you have a lot more of them. And you also have much higher energy ones, TeV neutrinos, for example, which then have higher cross sections. And so this is really the way to detect a collider neutrino, is to put a detector in the far forward direction, which is exactly where FASER is. If you can do that, you can actually open an incredibly interesting new world of LHC neutrinos. I mean, there is no such thing as an LHC neutrino program right now, but what I'm saying is that there will be in a matter of years. The neutrino energies are TeV, so the highest human-made energies ever. If you take out Ice Cube, they're just the highest ones ever, period. But they're incredibly high energy. And maybe even more interesting, every single flavor is produced. And so as opposed to, say, fixed target experiments where you're dominantly getting, new mu's, here, well, you're dominantly getting new mu's here, but you're also getting lots of new e's from kaon decay, even new taus from d sub s decay, and also neutrinos and antineutrinos. So basically all 6 types of known neutrinos are produced, and you can study them and do interesting, studies of lepton universality and all sorts of other interesting things that you can't do with simply one flavor of neutrino. So this is something we're very excited about, in part because we actually think that we have seen already these first neutrinos. So in 2018, as part of a pilot run, the FASER collaboration put this tiny box down in the tunnel. This is a 29 kilogram box of tungsten and lead, as you see marked here, along the line of sight, along the beam collision axis. We put it down there during one technical stop and pulled it out 6 weeks later during another technical stop, and collected 12.2 inverse femtobarns of data with this little box. And after a couple of years, we've of course been very busy building FASER, but finally have been able to come back to this. We've been able to analyze this emulsion data, and based on 11 kilograms of fiducial mass in here, so even half of this detector was basically thrown away, but with 11 kilograms of fiducial mass, we expect 3 neutrino interactions in here, just based on simulations. And just a few weeks ago, we put a paper in the archive where we announced the first direct detection of 6 collider neutrino candidates above about 12 expected neutral hadron background events. So, this is sort of like a 2.7 sigma signal. Here are two events, the displays of a neutral vertex. So basically the idea is nothing charge is coming in, but a bunch of tracks are coming out. And this is characteristic of a neutrino. It's also characteristic of a neutral hadron. So you have a background here. But basically based on a number of sort of characteristics that can differentiate the hadrons from the neutrinos, we can separate them and we have a slight excess. So this is, by no means the discovery of collided neutrinos. This is not a 5 sigma anything, but it's extremely promising because, we're already getting a few neutrino candidate events. And for example, this detector is so small, it can't even detect the high energy muon that's coming out of here. And so when we can, unambiguously detect that, that will be a huge way to differentiate signal from background. And so this is just a very preliminary analysis based on this detector using recycled parts. But to try to just bring that home, I think this is sort of a watershed moment for far forward physics. This FASER pilot detector was suitcase sized, something you could carry on the plane with you. We put it down there for 4 weeks, cost $0 because it was basically recycled parts. And we've already got 6 neutrino candidates. All previous collider detectors, which of course are building size, took decades to run, billions of dollars, have 0 neutrino candidates. And so it just shows the sort of promise of this interesting location in the far forward region. And so we have now started building FASER new, which will do this properly, not just based on recycled parts, but actually a small little 1-ton detector in the front here. It's designed to detect neutrino of all flavors. It's an emulsion detector, basically 25 by 30 centimeters by 1 meter long, and has a 1-ton mass. And basically we take this emulsion and swap it out every 10 to 30 inverse femtobarns for a total of 10 times during run 3 and analyze the tracks in it. And this slide here shows what we expect. We expect to detect about 10,000 new mu candidates, neutrinos, and 1,000 new E, and even 10 new taus. These are plots of the different flavors where we have the neutrino energy on the x-axis and a cross-section measurement on the y-axis. And for example, new mu's, you see that this is sort of the energy spectrum of neutrino interactions we expect to observe in FASER new. And so it's peaked at the TeV energies, which is exactly in this window where there's basically no data right now. So you have IceCube up here, you've got a bunch of accelerator results down here, no collider results ever, and the collider results basically interpolate between those. So it could be very interesting. And there's also new E, and as I say, even new tau, where we'll be able to sort of double or triple the world supply of new tau events. One thing that is developing now, and I think there's a large room to grow here, is the interest in the FASER new measurements from the QCD community. And again, for lack of time, I won't go into this in great detail, but obviously, if you are producing new mu, new E, new tau from these mesons, you have some sensitivity to how many kaons and how many D mesons are being produced at the LHC. And so, this brings up all sorts of interesting questions having to do with the charm production in the forward region, intrinsic charm, what's the distribution of strange quark momenta in the proton. These are regions of parameter space where existing simulations are sort of notoriously poor. And so this will provide refined data to refine these sort of famous simulations. And this will be very interesting. One that I'm very high on right now is it provides essential input to astroparticle experiments. So for example, IceCube is looking for stellar neutrinos and basically is hindered by the fact that it can't tell the galactic, extragalactic neutrinos from the atmospheric ones, basically because of this intrinsic charm or charm content problem. And we should be able to basically clear that up and remove that systematic error for ice cube and potentially open the window for them to really unambiguously find sterile neutrinos. Okay, so in the last minutes, let me go to the forward physics facility. So FASER, FASER-New, and other proposed far forward detectors, so critically S and D, which I had on the last slide, but don't have time to talk about. These are all quite interesting. We're already getting results, but we're completely constrained by this tunnel infrastructure that was left over from the LEP days. At the same time, it's becoming clear that there's a rich physics program. It's no longer just simply long-lived particles or FIPS. It's, neutrinos, Monte Carlo generators, and as I'll show, milli-charged particles, dark matter detection. So there's a huge program here. And I think this strongly motivates creating a dedicated facility to actually house these far forward experiments in the high luminosity era. So this facility is the forward physics facility. The SNOMAS process, we had a letter of interest where 240 authors signed on from very many different communities, as you would expect, given all these topics here. We've had 2 meetings already, which have been extremely interesting. I'd invite you to go look at these Indico pages for the talks. And we're planning a first paper on the physics potential, the FPF, which will be done within a month or so. And then a much larger SNOMAS white paper that can be completed in the SNOMAS timeline by February of next year. So what is this thing? So, here is a aerial view of Atlas and, the CERN globe and all that area. So here's Atlas. Here are these existing caverns. So the LHC goes along here, and then there's these caverns. This is where S and D is going to be. This is where FASER and FASER-New are. And if you want to put a facility on this, you want to put it on this line of sight, which is along this red dashed region here. And so work is proceeding along this direction, very actively, actually. So there are 2 main ideas. The first is to simply enlarge this cavern where FASER and FASER-New are. You basically have to push back this wall by 2 to 4 meters and to stay on the line of sight. And you can do that. This is called the alcove option, because for various rock structure, civil engineering reasons, you can't just simply push the entire wall back. You need to push it back in alcoves. So that's one option. The other option is to basically go to this open field site and construct a new shaft, a new cavern. And this is the latest, greatest plans from the civil engineering group at CERN. Kinsko Balazs's talk is really interesting from there. And basically the idea is to just dig a new shaft and put a new cavern down along the line of sight here. You can, of course, then make it fairly long. The current plans are 60 meters. And it has a lot of advantages because one can just work on the experiments here, irrespective of the LHC schedule, more or less. So this new shaft and cavern option is sort of some drawings are shown here. Obviously, it has a lot of advantages. You can go down there and work on these experiments. You have lots of room. Here's, FASER-2, upgraded, enlarged FASER-New and S&D detectors, Millikan-like detector, which is, as I'll show you, quite interesting, and even a liquid argon detector, which we're discussing now, which might be extremely interesting for both neutrino and dark matter physics. And the shaft here and even surface buildings are being designed. Maybe the most interesting for many of us is that a very preliminary class 4 cost estimate was just released. And this new shaft and cavern estimate is 23 million francs, which has significant error bars on it. But at least from my point of view, is remarkably affordable, given that you're digging an entirely new facility here. So let's see, sorry, how many minutes do I have left, if any?
Yeah, I think around 2 or 3.
2 or 3 minutes, okay, thank you. So let me just say what this forward physics facility could do. It's really a facility to house a number of experiments, not just simply one, but FASER would be presumably one of them, the upgrade of FASER. So here's this list of PBC benchmark points from 1 to 11. So this is by now, I guess, a very famous list. And here's an extra one, BC1 prime, which is a U1 B minus L gauge boson. But anyway, FASER can cover new parameter space for roughly half of these. FASER 2 is able to do a lot more. But what I think is really interesting is that recently work has found that the FPF can also facilitate working on milli-charged particles and also this dark matter or invisibly decaying dark matter, dark photon scenario. So let me just quickly try to explain some of these most recent developments. So BC2 is a milli-charged particle scenario. And as you all know, the Millikan experiment is targeting these scenarios, these models, right now with an experiment that's near the CMS interaction point. Here's the Millikan demonstrator, which is already proven that they can probe new parameter space. So that's pretty remarkable with just such a small detector. Frugi-Abari and Kling and Tsai entertained the idea of what if you took Millikan and put it in the far forward region, and they call that detector Formosa. And the basic point is that if you had, Millikan probing somewhere like here, if you simply move it, the exact same detector down to that far forward region, you can probe more parameter space because these milli-charged particles, just like a lot of weakly interacting light particles, have a much larger flux in the forward direction. So there are interesting background issues to think about, but in terms of just certainly the signal rate, you can win almost an order of magnitude in the charge that you can probe just simply by putting this in the far forward direction. So I think a milli-charged particle detector in the FPF is certainly a good idea, something that needs to be thought about more. Another idea, which I investigated with Brian Battelle and Sebastian Trojanowski, is this invisibly decaying dark matter scenario. So you have, pions, which make, say, a dark photon. But unlike in the visible cases, the dark photon decays to the dark sector. So it goes to dark matter. And so it decays invisibly. And this is in some sense a much worse scenario. Obviously, it's harder to detect these dark matter particles than E plus E minus, but it's not impossible because this dark matter can scatter off a detector. And the point of this study was that basically the LHC, through this mechanism, could be producing an extremely intense and collimated beam of dark matter particles. And so maybe you can detect them in a far forward facility. And so we proposed a new detector, which we call FLARE, for forward liquid argon experiment, basically a 10 to 100 ton liquid argon TPC, and found that in this parameter space, this model, this is the dark matter mass, this is basically the coupling, you could do amazing things. So in this plane, the gray is again excluded by current experiments. In fact, even maybe a little bit, this black is excluded too, depending on how much you're willing to trust theorist recasting. But the black thick line is the relic target where you have the right amount of dark matter. Down here, you have too much dark matter. Up here, you have not enough. And this blue contour basically shows the coverage of FLARE. And so the point is FLARE can cover much of the cosmologically favored region. That is the region where either you have the right relic density or you have less than the right relic density, which is of course also allowed. So this liquid argon detector is being actively investigated as well for another possibility for the FPF. So let me stop. The point here, I guess, in this talk was that neutrinos and light and weakly antimatter particles can be probed by experiments that can be done pretty fast, pretty cheap, and pretty small in the far-forward region. For FASER and FASER new, I think of this as an achievement, but also you could think of these as sort of prototypes for what's to come. It took about 4 years. The total cost was less than $2 million, and these things are 5 meters long, but we're already ready to start data taking in 2022 when Run 3 turns on. The Far Forward Physics Facility is a proposed facility to house a suite of far forward experiments, ideally to start when the high luminosity era starts and run for 10 or more years. And in that facility, this flare is, I think, something that is gaining interest. This liquid argon experiment could in principle do some very interesting dark matter searches and also neutrino physics. So that's something that I think is a growth area, and something that something to look for in the future. So thanks.
Yeah, thank you very much for this nice talk. So questions, please.
I ask one. Can you show the previous slide? Yeah, this one. I mean, you mentioned that you will cover, physical interest in a region where there is a prediction for the dark matter, okay? But here is written that Na64, this dotted line, should it, I mean, I would expect it before this liquid argon option.
Yeah, so, I mean, that is probably the most serious. Right, very good. So Na64 has a projection to go along here. So yeah, so we cover more range up here, but down here, if they actually do that, then that will already be covered.
Okay.
There's, I guess, two comments. One is that, of course, if you only do experiments which cover regions that no one else says they're going to do, you're kind of cutting yourself short. So of course we have to actually plan on things, and if we can all do them, that's great. The second point I want to just make, though, is that a lot of things here, for example, LBMX also, which cuts in even greater sensitivity, are quite different in the sense that they are sort of looking for missing energy, missing mass, and so don't actually detect the dark matter. Whereas we're actually, if we found a signal, we would actually see a scattering event, which would actually be sort of the direct detection of dark matter. So of course, one has to sort of view these contours with a little bit finer precision to understand what they all mean.
Okay. May I ask one more question?
Mm-hmm.
When you mentioned this neutrino program, would it be possible to, to observe Antitau neutrino?
Yes, it certainly would be.
Antitau neutrino, okay.
Yeah.
Because it's the only particle of the standard model which we, officially did not, how to say, not observed yet. Yes.
Yeah. No. Exactly. That's very interesting. So, let me go back to. Let's see where here.
Yeah.
So, well, okay. Well, so okay, at FASER new, I'm not certain of this. We should get, roughly 10 tau neutrinos and about 10 anti-tau neutrinos. But what I was mentioning, where I'm sure we would see it, is the FPF, because with these larger detectors, we should be able to see about 1,000 tau neutrinos. Now, how do you tell the difference between tau and nu tau and nu tau bar? There's a number of ideas on the table. One is simply, of course, that now you have a neutrino detector followed by world-class magnetic spectrometer, FASER 2, right? And so if you have the tau decay to muons, you can tell mu plus from mu minus. And so you can get a handle on it that way. An even more ambitious idea, which is really not is just in the infancy, but is this idea of even a magnetized liquid argon TPC, where in principle, you might not even need FASER behind it. You could just have a magnetized detector and distinguish new and new bar events, including new tau events. So that's even more ambitious, but either way, I'm quite confident that, yeah, we will see new tau and new tau bar. And of course, all the interesting things that come with leptogenesis and, primarily influencing the third generation, all these sort of things are very interesting to be able to distinguish the particle and the antiparticle.
Okay, thank you.
Yeah, thanks.
There was a question by Marco, but okay.
Yeah, basically it was answered already because sorry, my question would have been how to distinguish the different types of neutrinos, but I think you just explained that, so thank you.
Yeah. So the reason, so the FASER knew we'll be able to distinguish the different types of neutrinos, and that's exactly what suggested the emulsion technology. So you might know, emulsion technology is sort of last century technology. It's sort of old fashioned in the sense that, there's no timing at all. So you put the thing down there for a month and you take it out and all you see is a bunch of tracks. And so in some sense, it's sort of old fashioned, but the flip side is the spatial resolution is just absolutely incredible. And so you can actually see, D-meson tracks in this thing, and you can tell the difference between certainly nu E, nu mu, nu tau. And so it's a very good detector for separating the different flavors. And so that's in fact why we have an emulsion technology there.
Thank you.
Oleg, yeah, there was a question by Oleg.
Yeah, this is related to this liquid argon TPC idea. I was wondering where exactly the need for liquid argon is. In principle, you just outlined this emulsion idea, and that should also do the job, especially if you put magnetized iron around, you have a big magnetic field. That's it.
Right. So I'm quite a big fan of emulsion now, but I can mention just two things. One is that when we go to the high luminosity era with the increased luminosity, and not only increased luminosity, increased instantaneous luminosity, right? You can do the calculation and you basically have to pull the emulsion out with a frequency of like about a month. And it's not clear that, technical stops will happen that frequently. So it's, we would have to sort of probably influence the LHC schedule. And of course, it's an uphill game trying to tell Atlas and CMS what to do from your little small detector and small collaboration. The second thing is, of course, if you want to pull it out every month for 10 years, that's a lot of emulsion. So it requires a very high speed scanning facilities, which we probably do have, but it consumes almost the world's supply of scanning time. And second of all, it's very expensive. So FASER new is being constructed at a cost of less than $1 million francs. Very preliminary, just scaling it up. FASER new 2 would have to be probably 30 million. So it gets expensive. So that's one answer. But the other answer is that there's also this very problematic muon background that we have that comes through. And to make a long story short, at FASER, at the high luminosity era, it starts becoming such a problem that if we can't identify the incoming muon with the, the scattering that comes with it, it starts becoming hard to separate out the background. And so the fact that at a liquid argon, we can use timing and see, when that muon comes and the resulting scatterings, that's a very big help. And so I think liquid argon has a definite advantage just in terms of rejecting that background.
The timing, yes. And where do you get the first timestamp from? I mean, we will not necessarily have muon detectors in such a forward region.
So do you mean, I mean, it is true that we will combine data with FASER probably, so that will be sort of a muon detector. But do you mean in coordinating with the, I mean, we also do need to know bunch crossing times. We're hoping to get that from Alice. Yeah.
Yeah. Well, that's precisely my question. So essentially, what is your first timestamp for using the timing for the muons? And to know that in event X, muon.
Oh, I see. Well, we also have scintillators in the detector. So that gives a timestamp.
Oh, yeah, okay. So you just use the upstream detectors. Yes, your liquid argon was at the end. Okay.
Yeah.
Okay, cool.
Along the same line, Jonathan, if I can I ask you if the situation of the background in the forward physics facility is better or worse than in the current FASER location? Assuming in the high Lumi era. So what? Right.
So roughly speaking, the flux is about the same. You know, so this is 610 meters from the IP as opposed to the current ones, which are 480. So it's, you know, another 130 meters away, but roughly speaking, it's not that different. The problem comes when, you know, you have bigger detectors. And so of course you collect more muons. And so just the background rate is higher. Probably the most interesting thing to say though, is that we're exploring the idea of a sweeper magnet. So one, you know, nice idea is, so let's say we have the new cavern possibility out here. Then you have a number of places where you could put a magnet to just basically sweep away all the high energy muons. The most obvious is right here. There's a place where the line of sight leaves the beam pipe, but not the beam tunnel. And so it leaves the beam pipe. There's, you know, some room in the tunnel where you could put a magnet and sweep away the muons. And that's quite nice because then they still have, you know, roughly 300 meters to go. So you have quite a long lever arm to move them out of the way. Another possibility would be to, you know, go where SND is right now and put it there. There you have a smaller lever arm, but of course, then you don't have to mess around with the LHC magnetism. But anyway, that's an idea that's being explored. And I can say that it seems quite feasible in terms of the cost of making this magnet. You just need just a big iron magnet. You don't need a hole in it even, you know, you just have a big, big magnet. The critical question is, you know, can you put it here without messing up LHC, cryogenics and things like that? That's a little bit more troublesome. Yeah. But I suspect, my guess is that if this FPF in the new cavern is built, you know, given the significant cost and commitment that would take, I think probably there will be a sweeper magnet before it, which will also be a huge help in reducing all those high energy muon backgrounds.
Thank you. Thank you.
So, are there more questions? Yeah, if not, let's thank the speaker and all speakers of the session.